Before we go on in chapter 13, I wanted to take a few minutes and review what we've learned so far about line integrals with you. So this material that I've put on this handout so far is from sections 13.1 to 13.4, although I'll be adding material to it. So far we've talked about line integrals, and then we also did 13.5 where we introduced the divergence and the curl of a vector field. Put 13.5 out of your mind for now, and let's just review where we are so far. So we have different kinds of line integrals. There's line integrals with respect to arc length. And for those integrals, there's only one thing to do. If you have a line integral with respect to arc length, you see a ds where s is a little s. And you simply, there's no tricks, there's no theorems. That's the formula. You plug in r of t into f, you multiply by the length of r prime, and you work it out. That's it. Similarly, line integrals with respect to x and y and z, you plug the parameterization into f in all four of these cases. For x, y, and z, though, instead of multiplying by length of r prime, you multiply by x prime, y prime, or z prime. These, typically speaking, can be a little bit easier because you don't necessarily have a radical involved, so that's nice. I will mention that there is a connection between these guys and the line integrals of vector fields. If you add this one plus this one plus this one, if you add them all up, then you can actually get the line integral of the associated vector where each of these different functions here is the components of f. And I don't want to confuse you too much, so I won't say more than that. Go back in your notes and look that up real quick and make sure that you know the connection where if you sum up the parts here, then you can actually view this as a line integral of a vector field. Okay, so in general, having said that, line integrals of scalar functions, if you're integrating a scalar function, then there's really no tricks. You always plug in your parameterization and then you multiply by either x prime, y prime, z prime, or the length of r prime every time. That's it. No theory, no theorems. Plug it in, go. Okay? Line integrals of vector fields, the definition is right here. In general, the definition of the line integral of a vector field f, we usually write it dot dr along our curve C. You plug in the parameterization just like before, but instead of multiplying by length of r prime or by x prime or whatever, you dot product. That's a dot product with the vector r prime. So that's how you work those out. So really, even though this particular line integral of a vector field is different, it's a different flavor, the definition is not that different from line integrals of scalar functions. You just are dotting here, and you end up with a scalar after you take the dot product. However, we have several theorems for line integrals of vector fields, and I want you to realize that these three theorems that we're going to write down have everything to do with line integrals of vector fields. Okay, so here's the first one. This is one of the most important. Well, they're all important. If f is conservative, and that means that it's the gradient of some scalar function, so we'll just assume it's the gradient of little f, then you know that the line integral of f along C is just f of plug in the endpoint, f of r of b, the endpoint, minus little f of the beginning point. Really nice result. And a corollary is just a result that follows from a bigger result. So this immediately implies that, hey, if C is closed, these 2 points are the same, and so you're going to get 0 here, and that's all this is saying. So you really want to know those. When you're conservative, life is good. You just find the potential function, and if C is closed, then you don't even have to find the potential function. You just know the answer is 0. Keep that in mind. When C is closed, and you can check that f is conservative, you don't actually need the potential function itself. You just know the answer is 0. Otherwise, you have to do the integration tricks that we learned to figure out the potential function. Green's theorem applies really when f is not conservative. It applies when it's conservative as well, but you know the answer. You're just going to get 0 because C is a simple closed curve. And so the idea is Green's theorem is useful. This guy is useful, most useful, when f is not conservative. And when you're not conservative, this won't be 0 right here, q partial x minus p partial y. Key detail with Green's theorem, it only applies to two-dimensional vector fields. All right? And your curve C lives in the xy plane. And so this allows you to switch your line integral of f along C to a double integral. If this is your curve C, then you have the region inside. This is your D. You can switch the line integral around the boundary to a double integral over the interior of this. And as we've seen before, depending on the problem, it can be easier to go this way or maybe to go backwards and go that way. It just depends. So those are the tricks that we've learned so far for line integrals. And as we dive into the next two sections, we're going to be learning about parameterizing surfaces, and then we're going to learn about surface integrals. And the good news is that's the last kind of integral. We're going to learn about line integrals and surface integrals. There's a lot of similarity, and then that's it. We're just going to see some theorems that connect them together. So really, two sections of full-blown new material, and then two brief sections of weaving those things together, and then we're done. So God willing, you guys are going to see the end of your calculus book. I'm excited about it, and just encourage you to persevere through these next week and a half or so. I know you're getting pummeled with work, and I know this is difficult, but hang in there. We're going to get it. We're almost done.